type of geometry in the 21st century. When I looked at it, I decided that was really impossible to talk to you. So it's a bit like when you go to the cinema and you expect to see Gone with the Wind, and instead of Technic Hits, you're going to see Charlie Chaplin instead. So I'm going to give quite a different talk. Later on I can explain why I couldn't give another talk and why this is a more suitable talk, but it's a totally different kind of talk. And it's a talk about an old friend, the icosahedron. And I've given it a historical flavour from Plato, these are the Platonic solids, to the present time, because the icosahedron plays a very important role in mathematics throughout the centuries. It keeps appearing differently one form or another in a remarkable way. That's what's one of its interesting things. It's also a beautiful thing by itself, and the ways it appears in different parts of mathematics is itself fascinating. So that's really why I've chosen this topic. It unites the past and the present in a beautiful way, and it allows us to talk about many different things. But now, if you don't remember exactly what Plato looked like, here is Plato. Oh, it would be, yes, I can't get all of them, unfortunately, no. as envisaged by Raphael in the famous picture of the School of Athens. There were a lot of others who we cut out of the picture. He's raising his right index finger and symbolic fashion. Now, the icosahedron itself, as all of you will know, is a regular sided figure made of triangles, and there are 20 triangles, and you can count up the number of edges and vertices, and check Euler's formula, and things like that. The important thing is that you can colour it with 5 different colours, as exhibited here. And the colours are so arranged that at every vertex, all the 5 colours appear. And no two colours are the same colour are contiguous. Now, this is an important part of the geometry of the icosahedron, because, well, you see that the 5 colours are made even more clearly if you would try to make an icosahedron out of paper. What you do is you make a template, cut it up, you put it down, and then you bend it and stick it together. And there are the colours, and you can see exactly that each vertex there are the 5 different colours. Now, the important thing about icosahedron from the point of view of mathematics is a symmetrical object. That always was beauty. Beauty in this case means symmetry. You can turn it around lots of ways, and it reproduces itself. And every time you turn it around, you get a symmetry, and the symmetry is what form what we call a group, and the group of symmetries of the icosahedron is essentially an interesting aspect. Now, every time you move it around in a symmetry, what you do, of course, is you have to, the colours of the triangles get permuted. So this situation of the icosahedron is that it has a symmetry group, which is a group of order 60, because each vertex, there are 12 vertices, and at each vertex you can turn around through an angle multiple of 5, so you get 5 times 20 is 60. 5 times 12 is 60. And this is a subgroup of the rotation group. It's a finite subgroup of the group of rotations in 3 space. Now, it's a very important known fact to physicists and topologists alike that the rotation group in 3 space is not simply connected, but it has a double covering group, which has different names. It can be called spin 3, because it's generalized for all dimensions. It can be called also the same as SU2, the group of 2 by 2 complex matrices of determinant, unitary matrices of determinant 1. It can also be thought of as the unit quaternions, the 3-dimensional sphere in 4-dimensional space, given by union of quaternions, taking their norm into 1, like a circle is the unit complex numbers. All of these are the same group, and they're important ways of thinking of it. If you have any finite subgroup or rotation group, you can look at all the elements lying above it, in the double covering, to get a group of twice the order. So if I denote by gamma hat this double covering, it's a group of order 120. Now, because when you rotate the icosahedron, the 5 colours get permuted, you get permutations of 5 things from the symmetry group. The symmetry group has order factorial 5, which is 120, but that's not the same 120 as the other. Little catch. Because the only permutation you get when you do this thing round turn out to be even permutations. Those are half of the total of 120, and they give you 60. Those are the group. That's the subgroup. That's the group gamma. The group gamma hat lies over it, and is group order 120. But you see where the gamma hat is group above gamma. symmetric group is a group that includes them. They're not, they go off in different directions. So they're not the same 120, but the 60s are the same. And so the famous result is that the alternating group of even permutations on 5 things, is isomorphic to the group of the symmetries of the icosahedron. That's the modern description of the group of symmetries, and of course its history is long, came before the theory of groups. But the conclusion is that this group, A5, or the group of symmetries of the icosahedron, is what's called a simple group. Now, don't be deceived. A simple group is nothing simple about it at all. It's the most complicated thing. And it's a bit like physicists talking about elementary particles. An elementary particle is not quite clear what a particle is, and it certainly isn't elementary. Elementary simply means a building block out of which you make complicated things. But the building block itself can be very subtle. So simple groups are actually very hard. And this is the first simple group. And that's what has special interest. You start from the beginning, the first 2 groups you get are not simple, but then, hello and behold, you hit this famous simple group which appears and reappears all over the place. And one place where it appeared very famously is, of course, in the theory of polynomial equations, when you try to solve equations like quadratic equations, cubic equations, chordal equations, squinting equations, and so on, using square roots, and cube roots, and fifth roots. It was, of course, famously discovered that you can't solve the equation of degree 5 or more by radicals. 2 equations of degree 2 you know how to solve, 3 is more difficult, 4 is even more difficult, but you can do it. 5, nobody can do it. And then, of course, the famous, probably the most famous episode in the history of mathematics was the discovery by Abel, and then subsequently reinterpreted by Galois, that you cannot solve equations of degree 5 in general by radicals. This is, say, one of the highlights of mathematical history. Now, this is, on the one hand, you regard pure algebra as a theory about the groups and the groups of permutations and the roots of an equation, but it has geometrical consequences as well, because this group appears as the symmetries of the icosahedron, you can see it embodied in geometry. And the consequence of that leads you to the famous Poincaré fake sphere. If you consider the 3-dimensional sphere, nice round thing, ordinary space with a point of infinity added, then inside there is a group. Inside there is a subgroup, group gamma. Sorry, gamma hat. There should be a hat on that. I think I can put a hat on this transparency here. I can make my correction. And so the quotient of that group is in fact the same as so true with a few hats here and there. This group gamma being simple means that when you abelianize it, then you try to make everything commute, you get nothing left, it becomes 0. And if you have a manifold whose fundamental group can't be abelianized, well, if you abelianize the fundamental group, it's known in homotopy theory that what you get is the first homology group, which is something much simpler. And if you abelianize this particular 3-dimensional manifold of Poincaré fake sphere, you get no homology. On the other hand, the manifold itself is not the sphere because it has a non-trivial fundamental group, this group gamma. And this was the famous source of a famous discovery, mistake, whatever you like, of Poincaré, who originally thought he found this space was a sphere, but he realized there was something other than homology, which was the only tool available in those days, and he invented the fundamental group to explain what was going on, and that's the beginning of modern homotopy theory. So this has a very important role in the history of topology and geometry and so on. So right at the beginning, or not in Plato's time, but already at the beginning of the 20th century, the geometrical aspect of the icosahedral group is very important, just as the algebraic side was important in solutions of equations. So now, I believe in showing pictures of mathematicians who've done it, because it shows you that mathematics is created by people. And that's how, they're not abstract things just in books or papers, they're creations of individual people. Sometimes very interesting people, very colourful people. So here is a picture of Niels Henrik. Well, I can't get the dates on the bottom and the currency at the top, but move it up and down. Then his Abel's date, you see he died at a very early age of 27. And he is famous in Norway, and this is a picture taken from the 500 Norwegian kroner note, which is worth about £50, which I have on my desk. I hope nobody steals it. It's a very nice picture of Abel. When you die very young, not many pictures are left. And Abel has that one, but his even younger colleague Galwa has left only been left a kind of pencil sketch, which is even a dubious authenticity. There is Galwa. So the two creators, they are in a way two of the founders of modern mathematics. That from there onwards, mathematics took a different line, became much more general, it moved in a new direction, but it is still with us today. And while we're about it, we might as well look at the picture of Henri Poincaré, who was a famous mathematician at the beginning of the 20th century, and did an enormous amount of mathematics all over the place, not just in the connection of this particular problem, but I mentioned him in connection with the Poincaré sphere, the fundamental group, in his role in topology. He is a very, very big figure. Now, let me move on. I'm going to keep this talk very elementary, as far as I can. And in that spirit, I'm going to talk about singularities of complex curves. So you start off with two complex variables, Z1 and Z2. And two complex variables, if you take the real imaginary part, you think of as four-dimensional Euclidean space. Inside there, you take the elements of norm 1. Some of the squares of the absolute value is equal to 1, which is a three-dimensional sphere. And in that four-dimensional space, you can take the two equations, Z1 equals 0, Z2 equals 0, each of which gives you a complex line in the complex plane. And each of these complex lines, which is a plane, real plane, reach the boundary, the sphere, in a circle. So in this circle, now this picture is meant to represent high dimensions. So the boundary is a three-sphere, these are planes, these planes meet the boundary in a circle, this plane meets another circle. So on the three-sphere, you have two circles in the two orthogonal planes. And these two circles, in three-dimensional space, you can verify are linked. The most fundamental elementary piece of topology is that two circles can be linked, you can't pull them apart. You do usually draw that in three-dimensional space here. It doesn't matter whether you have a point of infinity or not, the linkage is still there. So these circles are linked, and that's a very important fact. The complex property of intersections converts into the topological property of linkage. But the dimensions are different. You see, in four real dimensions, two planes intersect in a point. When you look to the boundary, that point disappears, and all you're left with is the circles, and what replaces the intersection of those two planes is the linking number of the two circles. These circles, by the way, you can take them, well, not only in the two planes, because you can take any direction you like, you get a whole family of circles which fill up the three-sphere, and that's what's called the Hopf vibration of the three-sphere and the two-sphere, very important part of topology. Any two of the fibers are linked. It's quite difficult to imagine. Just take this space here, think of it as enlarged with a point of infinity, draw lots of circles which look like straight lines, and they link each other. Every two link. They fill the space, no two intersect. It's actually quite difficult to visualize in three-dimensional space, and it shouldn't be called the Hopf vibration, because it was discovered by Clifford in the 19th century. But most things in mathematics are wrongly attributed. That's well known. That's a bit about linkage. Now, if you go from straight lines to more complicated things like algebraic curve, suppose you take a polynomial equation, f z1 z2 equals 0. Then which describes a curve in space, complex curve, and that will cut the three-dimensional sphere again on curve. I'm thinking of the point of the curve where the curve goes through the origin and it has a very complicated singularity. Two lines form, if you like, a usable curve, and then they meet the boundary in these two circles, which is not easy. A complicated algebraic curve will meet the boundary in something one-dimensional, which in general are not. Or it could consist of many components, in which case you also say it's a link. So links are not put together. If it's only one component, it's a knot. If it's more than one component, it's a link. But in general, think of it as a case, if the polynomial is locally irreducible, then you'll get a knot. Now take examples. Take the simplest examples you can think of. Write down z1 squared plus z2 cubed equal to 0, and what you get, the knot you get is a trefoil knot. If you write z1 to the p plus z2 to the q, the the knot you get what's called a PQ knot on the torus. You take a torus, which you can think of as sitting inside the space where you put mod z1 equal to 1 and mod z2 equal to 1. And then this knot, can be drawn on the surface of the torus, and it winds around P times one way and Q times around the other way. And that describes a certain kind of knot. P with 2, Q with 3, you easily see will reproduce the trefoil knot. So these are knots that you can see which correspond to the singularities. So singularities of algebraic curves, which are something you can see algebraically. But then what does it mean? Well, here it tells you what it means topologically, that you get away from the singular point and look at what you have as a knot. The knot captures the essence of the singularity. And so there's a very close relationship in general, this is not just these examples, between algebraic singularities, which we describe by polynomial equations, and the complicated topology of things like knots. And from that's the beginning of course, a long story which relates to geometry and algebra. Now let's go up in dimension. Let us go up from dimension 1 of curves to dimension 2 of surfaces. You always have to think carefully when you're thinking about real or complex dimensions. If I talk about algebraic objects, it's complex solutions, and the real number of dimensions is twice that. So an algebraic curve is a surface in real geometry. An algebraic surface is a 4-dimensional. So you have, to get a surface, you take three complex dimensions first of all, 3 complex variables, write down a polynomial equation in z1, z2, z3, equal to 0. The solution to that will form an algebraic surface in 3-dimensional space. And then you can look near the origin, supposing the origin is an interesting point, and around the origin you will have a unit sphere, which will be a unit sphere in 6-dimensional space, and so it's 5 dimensions. And there you write it down with the equations, of course, equal to 1. It is 1, yes. And you intersect that, and what you will get now is a 3-dimensional. Yes, I've used sigma for the complex surface, m of sigma for its boundary. So m sigma itself would have 4 real dimensions, m of sigma would have 3 dimensions. So this is the one step up from the knot. Instead of getting 1-dimensional thing which is not, you get a 3-dimensional manifold. And now this 3-dimensional manifold, in the case of 1 dimension, every 1-dimensional manifold is a circle or a union of circles. But in 3 dimensions, life is more difficult, more interesting. So the example, and I don't pick this one out of a hat, I pick it from Alice aforethought. Namely, take the equation z1 squared plus z2 cubed plus z3 to the 5th. And that's, you draw that algebraic surface, you intersect the sphere, you get a 3-manifold, so we give that manifold a name, we call it M235. And now, miracle of miracles, beauty of beauties, that M235 is the Poincare sphere. Now that's spectacular, I mean, that's pretty impressive. I mean, see that for the first time. Well, how did this happen? Where does it come from? What does it mean? So the first thing is, why 235? You know, I could have written down any numbers. Why on earth does 235 have to do with the Poincare sphere? Well, first clue is, you notice that these are the primes that divide 60. 60, the order of the icosahedral group. Well, that's already a good start. You know. Prime factors are important. Second thing you might notice is that if you sum the reciprocals of 2, 3, and 5, and I've done the sums right, you get 31 over 30. Just bigger than 1. That's important, and I'll explain in a moment why it's important. In fact, you see, imagine putting P, Q, and R instead of 2, 3, and 5. Unless P, Q, and R are all rather small, you're going to get a number here which is much less than 1. So to get numbers bigger than 1, you've got to take small numbers. This one is the last in the chain. One is the last, it's the one just above the threshold. So it's very uniquely determined. That's what part of its history. Now, to see the geometry of that, let us take the icosahedron, and let's pick a particular triangle on the icosahedron. There are 20 triangles on the icosahedron. Take one of them, and then draw the medians. So you get divided up into 6 triangles. Now, this is drawn on a plane. You have to imagine this as drawn on the curved surface of the sphere, curved surface. But you can still draw the medians and sections. You get the same sort of picture, and you get these triangles. And I was one of the concentrate on so one of these small triangles, which I labelled just by the symbol triangle, Now, the number of those triangles is, well, obviously 6 in each triangle, and there are 20 triangles, so you get 120 triangles. And again, the symmetry of this thing will act on all these things. Now, if you look at the angles of this triangle, I've labelled the vertices A, B, and C. You easily see that the angles A is 90 degrees, angle B is pi over 3, angle C, which is where you have the rotation to 5, is pi over 5. And now if you add up those angles using the formula above, you'll see that you get 31 over 30. Now pi, you take away the pi, which is what you get in a flat space, and you just get left over the area of that triangle. And this is, of course, an example of the famous theorem of Gauss, calculating the what's called spherical excess. In flat space, some of the angles of the triangle is pi, 90 degrees. On curved space, like the sphere, it's bigger than pi. And the difference, what's called the spherical excess, is beauty of beauties equal to the area, assuming you're on a sphere of radius 1. This was known by Gauss, maybe known as well as people. But it's a beautiful result, and of course it's a special case of more general results, which tell you about the relationship of the sphere is something of constant curvature. Is the curvature the same everywhere? You can rotate the sphere, or it's the same. But in general, if you have a wavy surface, you can calculate the curvature at every point, and you can integrate it over the area, and you get another number, and that is always the spherical excess of the angles. So assuming that your lines of the triangle are GJ6, the things that pass the shortest distance. This is a famous formula in differential geometry and topology. I think covers the course that has been taking place over the same medium. So this is a very beautiful result, and the fact that those numbers add up to just a bit more than 30 comes to play a role in measuring the spherical excess. So it's all hangs beautifully together. At the same time, as I pointed out, if you take, since I mentioned Gauss, we have to pay homage to the great man, and there is Gauss. Gauss is meant to be a rather difficult character. This picture is a very sort of sympathetic picture, a rather kindly old man. There's a little smile in his eyes. Whether it's artistic license or obviously it was a painting rather than a photograph, but not quite the character of Gauss that has come down to us other sources. But anyway, we give him the benefit of the doubt. Anyway, he was a great mathematician, whether or not he was a nice man, not a man. The two things don't always go together. Can't have everything. Now, as I pointed out, if you just, instead of taking the numbers 2, 3, and 5, you were to take a set of numbers P, Q, and R, which are bigger, then you would in general get number. I make the wrong way around, of course. If they were P, Q, and R were big numbers, the inverses were small, then you'd be less than 1. Now you get triangles, you get things which are related to the angles of hyperbolic geometry, and surfaces of negative curvature. The formula which relates the spherical excess to area works in both cases. It's the average integral of the curvature. If the curvature is negative, the excess is not negative, the excess is deficit. And so that you would get into hyperbolic geometry, which is the counterpart of spherical geometry, but it's negative curvature, more difficult to visualize, but very important too. But you don't get the ones of positive curvature unless you take small numbers, and P, Q, and R, 2, 3, 5 are the largest admissible small numbers that you can take. So that relates to geometry, the geometry of icosahedrons, angles of triangles, and so on. And now, that was just the top part. Then we move on to the bottom part of the transformation. Invariant polynomials. If you've got a group that acts linearly on the vector space, so this group acts on C2 because it sits inside the group C2, and therefore, if you take coordinates U and V, I want to keep the Z's for another space, then this will act by giving linear translations on U and V, and will act on the homogeneous polynomials of any degree. For example, quadratics or cubics. And a polynomial is said to be invariant, obviously, if it doesn't change by applying any element of the group. So, if it's written down formally, there it is, f gamma uv and f of uv, that's a strictly invariant polynomial. And now you can ask what polynomials there are. And in the particular case of the icosahedral group, where would you get invariant polynomials from? Well, if you have an invariant polynomial, then its roots thought of as these are homogeneous polynomials of two variables u and v. You can think of the ratio of u to v as one complex number, including infinity, and so you get a point on the root will be a point on the complex vectorial line, or essentially the two-dimensional sphere. And so this invariant polynomial will correspond to a bunch of points on the two-sphere. Because it's invariant, it has to be invariant under the group gamma, the roots have to get commuted. So an invariant polynomial corresponds, or made up, its roots will be made up of collections of things commuted by the group. Well, now we obviously can see how to get those. Some take your or edges, there are 30 edges, take the midpoint of an edge, take the 20 faces, take the midpoint of a face, take the 12 vertices, and now you've got 30 first set A, set B, third set C. So you've got 3 collections of points, which are each of which is invariant under the group. And now the numbers of these points give you the degree of the polynomial. So you get a polynomial f for the first one has degree 30, polynomial for the second one has degree 20, polynomial for the third one has degree 12. And you notice then that if you take f squared, g cubed, h to the fifth, they all have the same degree. They're all degree 60. This is really the opposite of the previous formula that say 2, 3, 5 divided by 60. So we have 3 invariant polynomials, all of the same degree. And now, it's a nice result. It's plausible, you believe me. Then it says, this essentially is all you can get. I mean, we use the icosahedron because this is the symmetry of icosahedron to find invariant polynomials. And you know, any other invariant polynomial would have to have to be raised to icosahedron. So the result is that these 3 polynomials generate all the invariant polynomials. Any polynomial that is invariant is a polynomial itself in f, g, and h. But on the other hand, there are 3 invariant polynomials and we only have 2 variables, u and v, so you might expect they're not independent. And that's true. They satisfy one relation. And the relationship is written down there. F squared plus g cubed plus h to the fifth. By the way, when I say polynomial has roots, the roots determine the polynomial only up to a constant. So of course the particular coefficient you put in front can change so there's no real significance. And the fact that these have coefficients 1 in front of them, if you change that, it wouldn't make any difference, rescaling. Anyway, that equation is the equation to describe the relationship between the 3 basic invariant polynomials, which comes out of the icosahedron. Now if you look at that, turn that equation into geometry, you see the geometric interpretation is that start off with a space of 2 complex variables where you put your coordinates u and v. Look at the space of 3 complex variables where you call the coordinates z1, z2, z3. And consider the map from the uv space into the z space given by the 3 polynomials f, g, and h, just as described. So you map C2 into there. Because they're invariant polynomials, any 2 points in C2 which differ by an element of the group give the same image. And so what happens is that if you divide C2 by gamma hat, the quotient, Coulom's relationship, to identify pairs of points which differ by the group, that gets mapped into or into the space C3. And what you see on the other side of space C, you get the equation of the surface we wrote down before, z1 squared, z2 cubed, z3 to the fifth, and what you check that this is exactly identical. The 2 sides are the same. The quotient of C2 by the group is the surface with exponents 2, 3, and 5 we wrote down. So that's the exact tie-up between that surface and the icosahedral group. Now, if you just intersect this with the boundary, then instead of having 3 spheres, you get the spheres, and sorry, this is the first one, the mistake here. Lots of mistakes before. No, sorry, this is something wrong with my eyesight on the screen. It appears that there is 3 and here is 2. This is a 2. And this is a 3. This is the unit 3 sphere in here. So the last line, the blue line, which you get by just cutting down the previous equation, which is the elements of the unit sphere, tells us that the 3 sphere divided by the group gamma hat, which we call the Poincare fake sphere, is in fact isomorphic as a manifold to the manifold which you get by taking the polynomial equation exponent 2, 3, and 5 and intersecting with the boundary, and you get the manifold M2, 3, 5. So this is giving you more or less a proof of the statement I made before, that the Poincare sphere does correspond to this particular equation. It's a very beautiful fact, and it's quite proved. Well, once you know the theory, all of this, by the way, would have been known and was known to another great figure of the past we have to pay homage to, Felix Klein, who was a geometer and algebraic, and this kind of area was very much his speciality. He wrote a famous book called Adhesion, which I would recommend people to look at. It's old, out of date in some ways, but all of this is in there, and in great detail. This was all known to Felix Klein. By the way, Felix Klein was also quite a dominating. He was a brilliant lecturer, but he was also quite a dominating personality. He was a powerful figure who imposed his personality on his associates. Now, I'm going to move to more general, other higher dimensions in general. General question here, which is about the relation of topology to smoothness. Topology is concerned with continuity. 2 spaces are topologically equivalent or homeomorphic. If you map one to the other one by a continuous map, the inverse is also continuous, so topologically they're equivalent. But you've also asked whether maps, if you're dealing with smooth manifolds, should be not only continuous but differentiable. And differentiable means a little of derivative. It doesn't matter, you can have infinitely many derivatives if you like. Smooth, you say. So you distinguish between continuous things, topological, and smooth ones. Now, that's a distinction we make nowadays, but in the past, people didn't think there was much difference between them, and it was certainly well known, and in low dimensions, that for surfaces, the 2 things were the same. If 2 surfaces were topologically equivalent, then they were differentiably the same. In dimension 3, that was also proved, but it was proved much later, proved in the 20th century. And then, surprise, surprise, mathematics is full of surprises, that's what makes it interesting. In dimension 7, John Milner gave a counterexample, showing that in dimension 7, you can get a 7-dimensional sphere, a 7-dimensional manifold, which was topologically the same, but differentially not. That was called an exotic 7 sphere. And this opened up a whole door, whole industry, trying to understand what happened, the distinction between continuity and differentiability in more than 3 dimensions. And in particular, this 7-dimensional sphere, if you take 2 spheres, you can cut little holes out of them, glue them together with a little tube, and make another space which is topologically still a sphere. I take 2 circles, cut them out, and make a bigger circle. But you can do that smoothly with differentiable ones, and then the exoticness can add up. It turns out that the group of exotic spheres is a group, median group, and a cyclic group, or 28 in dimension 7. This exotic sphere of Milner's is the generator of that group. So there's a whole beautiful story about this. But what I want to tell you now is what is the relationship of that with what we've been talking about. Well, first of all, I've got to use the transparency of John Milner. Unfortunately, the one that Andrew gave me is not a very good one. But he shows him as a young man. All the ones I recently showed him as an old man with a beard, and I thought you'd like to see that. He did this when he was a very young man. He became famous. He got the field medal for his discovery. And something's happened here. No, I think it's okay. It's okay. Hard to follow your own notes. Ignore the title at the top. This is. Well, no, sorry. It's a bigger one. These are something called Breeze-Cone spheres. Now, this is concerned with a relationship between algebraic equations and topology, just like we had before with the Poincare sphere, except we have more variables. We have higher dimensions. Now you play the same game in a very simple way. You take the equation we have 2, 3, 5, and you add a couple more squares onto it. And once you add a couple more squares, it looks a bit more symmetrical. You put all the squares together. So I've called the first 2 variables Z1. They're powers 3 and 5, and then the 3 variables which are all quadratic. And then you get a manifold, algebraic variety, which you denote by sigma with those exponents, C5222. It lies in C5, so it has 4 complex dimensions. And if you intersect that with the unit sphere in 9 dimensions, in 10 dimensions, the 9-dimensional sphere given by the equation, you get now a manifold which I will call, similar to what I did before, the manifold M35222. Manifold 352 was the Poincare sphere. So all we've done is put in a couple more 2's. Now, this has, first consequence of that is that for dimensional reasons you're rather trivial, whereas the Poincare space M352 was not simply connected, it had a fundamental group. When you throw in more room, the fundamental group disappears. This space is simply connected, and it has no homology, so topologically it's a sphere. But it is in fact the Milnor sphere, and differentially not the same as the Sandler sphere, so it is the exotic sphere. And this description of the Milnor sphere, Milnor gave a different description, was discovered by Beaskell some years ago, and it also generalizes. If you keep adding more and more 2's, dimensions go up 2 at a time. If you add it go up, then you get manifolds of dimensions, exotic spheres in dimensions 11, 15, 19, etc., etc. And these all generate cyclic groups of exotic spheres. The order grows up in an interesting arithmetical way, which is related to Bernoulli numbers. And Bernoulli numbers are one of why they come into geometry and topology is one of the beautiful mysteries which we've learned about, but it still remains a mystery. So there are the B-score spheres, and so I have to give you a picture of B-score. There is a nice picture of B-score. Well, I think he was a young man when he did that result. This is a more recent photograph I'm showing months this year. Now, that takes us up until the discovery of these exotic spheres in higher dimensions. We've gone out to lots of dimensions. In dimension 3, there's a different story. We've skipped over dimension 4, we've gone out to higher dimensions. And that was a situation regarded as normal in topology until Simon Donaldson, my student, came along. And Simon Donaldson, now this I'm going to be very quick about. Simon Donaldson, what's happened with the influence? Did I knock it? Is there a physicist in the audience? Somebody who understands the lenses.
It does automatically.
Oh, that's okay.
Oh, there is a physicist. It's the machine itself. Now, so going back to dimension 4, people thought that dimension 4 would be a bit like dimension 3, but a bit harder, and a lot of progress was made, and people thought it was just about finished. When, out of the blue, Simon Donaldson, was a second-year graduate student, dropped a bombshell. And relatively the bombshell, doors opened up. Bombs tend to open doors, you know. Sorry, that terminology. I get thrown out of the building with that. So it turned out in dimension 4, there are totally new and deep phenomena, which are actually much harder than the phenomena discovered by Milnor and Beaskell in higher dimensions, where there is a difference between differential and continuous things, but in dimension 4 it's there in a much, much deeper way. For example, it's now known that there are exotic, not only exotic spheres, but exotic fourth-dimensional spaces. Spaces which are topologically the same as flat space, but are not differentially the same. That is much more difficult, but as long as there's some topology, you can build on it. If there's no topology in the space at all, where on earth you start finding something to hold on to? It's very mysterious. Not only are there lots of these, there are uncountably many. So there's a whole world of exotic four-dimensional spaces, which is mysterious in many ways. And this 4 is the only dimension in which this is true. So the very unique property of about 4 dimensions is that statement there. It's really one of the deepest statements in mathematics you discovered. And we're still struggling to it, and we only understand parts of it. Now, this result about the flat 4-dimensional space is in some sense slightly misleading, in the sense that it's derived indirectly by working with 4-dimensional compact closed manifolds. And there the situation is interesting, but not quite so bizarre. Compact manifolds may have exotic structures, but they won't be uncountably many. We tend to be finite number. But anyway, there are. So the statement is, as well as Donaldson's work, is there are exotic, compact, 4-dimensional manifolds which are simply connected, and you take a standard example, find a non-standard example, But we don't know whether it's true for S4. For the 4-dimensional sphere, this remains an open problem. For the 3-dimensional sphere, it was solved recently by Perron, famous Poincare conjecture. In higher dimensions, it was solved before. But in 4 dimensions, it's still unknown, despite all the work of Donaldson and what's happened since. So that's still a big problem, but if you take 4-dimensional manifolds, which are a bit more interesting than the 4th sphere, then they have exotic structures. Now, where do they come from? Well, our old claims, algebraic surfaces. Take an algebraic surface given by some kind of homogeneous polynomial in 4 variables in predictive space, so only the ratios count. So in 4 variables in 3-dimensional predictive space, the surface gives you one complex equation, so it cuts down the dimensions from 3 to 2, it's complex dimensions, and so it's 4-dimensional real manifold. So here we have a large family of 4-dimensional real manifolds, which are derived by just writing down polynomial equations. Here are no singularities. It's a simpler story than studying singularities in a way, but it's very hard, and I'm sure you can try to do something, even with your computer, tell it to draw a picture of a 4-dimensional manifold given by simple equations. It doesn't know how to do it. So understanding the relationship between geometry and algebra is really what I'm talking about. Now, when you write down a simple equation, what is a geometric meaning? It is a difficult, hard problem of a lot of fascination. We talked about examples where you bring in fundamental groups, raised like heater and so on, it's one level. Then another level where you go to manifolds which have exotic structures, it's another level. They appear in higher dimensions. Here they're going to appear in 4 dimensions. The way they appear in 4 dimensions is a bit different from in higher dimensions. They don't form a group, they don't do anything like that. And one of the, I can't go into this because it's more technical, this is more recent work. But one thing you can say, if you take this surface, it cannot be cut in half in a sensible way, in a non-trivial way. And this, unlike curves, you see, if you take a curve, algebraic curve is a surface. Typically, it's a surface, you can draw a picture of it, like a surface with 2 holes, 3 holes, 4 holes. The holes are called the genus. This is a surface of genus 2. And if I take a knife, I just cut it across the middle there, in a circle, cuts it in 2 halves, each of which has only 1 hole. Every algebraic curve looks like this, and they can all be cut out into slices. They're all built up in a way out of the basic one of 1 hole, the torus, gluing together. But in 4 dimensions, that is fundamentally false. What was proved by Donaldson himself is that you take simple equations and you can work out the homology, which is telling you, roughly speaking, like how many holes it has. And they can be simply connected, there's no complicated fundamental group. And yet, you can prove that you cannot cut it in half. There are more precise statements, that gives you the idea. You cannot break it down into smaller surfaces, glued together. Basically each irreducible equation defines its own basic manifold, and you can't get that from anything else. So they have formed the building blocks. 4-dimensional manifolds include all the different algebraic surfaces with different degrees, essentially. So that's a very rich theory, and we're just beginning to explore it, and we don't know much more about it. So, well, at the end, this is more or less the end, except, of course, I have to show you a picture of Simon Donaldson. That's a recent picture of Simon Donaldson. When he did this work, I'm referring to, he was a second-year graduate student, aged about 23, probably. Here he is as a professor at Imperial College, and still going on doing important things. But that was his breakthrough, and he opened up entirely new areas in geometry and topology. But I didn't quite finish my statement about what Donaldson proved. While at the same time proving that you cannot cut an algebraic surface in half in an interesting way, you can cut a little piece of it, but that's not interesting. What you find is that it is true that algebraic surfaces can be cut along pieces, but those pieces can be things like the Poincare sphere. See, in dimension 1, the only thing you get by cutting it is a circle, or a union of circles. But in dimension 3, there are other possibilities. And one of the possibilities is a fake sphere. It looks like a sphere, first sight, so it's a good approximation to a sphere. So you're cutting it along some slightly bizarre sphere. It's a sphere with a fundamental group, in fact. So our famous Poincare sphere appears inside these four manifolds as the sort of thing which you need to glue them together. We don't quite know why. So, in a way, summarize the relationship of this icosahedron with all these things. You see, the icosahedron gave rise to the Poincare spheres, which are interesting manifolds, fundamental group. Higher dimension analogs by throwing in a lot of squares which give you exotic spheres, higher dimension. And they appear in their three-dimensional form as the things along which you can chop up 4 dimensions. Now, the interesting comment here is the following, that the original Poincare sphere has a fundamental group, the famous symmetries of that icosahedron. If you enlarge it by adding a lot of squares, the fundamental group evaporates because there's so much room and fundamental every knot can apply itself. And yet, somehow, the fact that there was a non-trivial fundamental group in that original thing you started with survived in 9 dimensions in terms of the exotic structure. It's transformed itself. Instead of being a topologist's plaything, it becomes an exotic differential structure. How it does that is rather fascinating. And here, in 4 dimensions, 4 is something similar. The 4-dimensional manifold is simply connected. These examples. But the 3-dimensional slice, if you cut it, will have a fundamental. Fundamental disappears in the 4-dimensional manifold, but it's tied up with the exotic differential structure. Some mysterious way we don't really understand, which these fundamental groups reappear higher up. But the way the fundamental disappears is a bit like with Cheshire Cat. The smile is the exotic differential structure. That's not an exciting kind of theory. The best I can do is an approximation. Well, I think I've probably not used up all my time. If anybody wants to ask me any questions. But I thought I'd keep to an elementary topic because this is the sort of thing you can explain, hopefully, reasonably. It deals with elementary things like polynomials, elementary geometry, symmetries, difference between smoothness and continuity. And yet it's very deep subject. We start as history, roots in the past, from Plato all the way through the work of polynomial equations to Harvard, Galois and so on, up to modern ideas about manifolds and exotic structures, higher dimensions, and it's still going on. So the icosahedron is still with us. And I like to think of these things like icosahedron as sort of beautiful little nuggets, diamonds. They survive, they're very hard to break it, and you keep using them time and time again as you get up more. Nowadays, people still use diamonds in industrial processes. In the old days, they use it for decoration. Well, the icosahedron is a bit like that. It's still there, it's still used, and it's dig beneath the surface. You can find it almost anywhere. Well, I think I've even finished using my transparency. I could have showed you a few more beauty pictures, but I think I'll stop there. Okay?
Are there any questions? You seem to have had all the answers. Okay.
One question. So the singularities in C2 were reflected in the link type or not type in the 3-sphere, and the singularities in C3 are being reflected in a 3-manifold.
Yes.
Does the way the 3-manifold is embedded tell you anything as well, or just a topological type?
Well, obviously, in the first case, you have a knot, nothing about the knot except where it's embedded.
Yeah.
The next case up, you think will also be embedded in some way. You're quite right. It is not. It has an intrinsic fundamental of its own, but the way it sits inside the higher dimensional basis is still interesting. I haven't thought about that. I haven't even studied it. But you're quite right. Both sides are interesting, both the internal and the positional structure in the other one, and they're all part of the same story. How do the algebraic equations tell you what's happening in a geometrical sense? And there's a very rich story there at all levels.
Anybody else? No, well, thank you very much.